Our universe should have instantly fallen apart. The fundamental laws of physics, in their raw form, paint a picture of a cosmos too fragile to last a single second. Yet here we are, in a stable reality filled with galaxies, planets, and life. This is the central mystery of cosmic stability, solved by the discovery of an invisible quantum field. By the end of this journey, you will understand the invisible scaffold that prevents everything from disintegrating into meaningless light. This field, called the Higgs field, is an all-pervasive presence that gives particles their mass. Without it, atoms could never form, stars could never ignite, and the very concept of matter would be impossible. How can a field we cannot see or feel hold the very fabric of reality together? This is one of the most profound discoveries in modern science, revealing a hidden layer of existence that keeps our universe intact. What does it feel like to know your stability is a cosmic accident? But to understand why this field is so vital, we must first redefine what we mean by nothing. In our everyday experience, a vacuum is simply empty space. It is a quiet, dark void, a place where all matter and energy have been removed. This is the classical view, a concept of true emptiness where nothing happens because there is nothing there to act. If our universe were built on this kind of nothing, its stability would be a simple, quiet fact. Yet physics has revealed this idea to be an illusion, a comforting fiction that completely breaks down at the smallest scales. The quantum vacuum is nothing like that empty box. It is not a void but a stage, and a deeply restless one. According to Heisenberg's uncertainty principle, it is impossible to precisely know both the energy of a system and the time over which you measure it. This fundamental rule of reality has a stunning consequence for empty space. It means that on incredibly short timescales, energy can appear out of nowhere, borrowing from the universe itself before vanishing again. The quantum vacuum is therefore a seething, bubbling sea of potential. Within it, virtual particle pairs like an electron and its antimatter twin, a positron, constantly flicker into existence. They are born from this borrowed energy, exist for a fleeting moment too brief to measure directly, and then annihilate each other, returning the energy loan. This is not a metaphor. These quantum fluctuations have real, measurable effects, influencing the properties of atoms and even the structure of spacetime itself. So the foundational layer of our universe is not a placid emptiness, but a chaotic, energetic froth. This is the first crucial piece of the puzzle. If the vacuum were truly empty and calm, the universe might be simple, but it would also be sterile and perhaps impossible. It is this inherent, buzzing activity of the quantum vacuum that makes the existence of more permanent structures, like fields and particles, not just possible but necessary. The question then shifts. It is no longer why is the universe stable, but how does anything achieve stability at all within this constant, underlying storm? The answer lies in understanding that in this quantum realm, the actors are not solid particles, but something even more fundamental. The true stars of this show are the fields themselves. Think of the entire cosmos as an endless, invisible ocean. This is not a metaphor for space, but a description of its most fundamental substance. We call these quantum fields. They are not made of anything smaller. They are the primary, irreducible ingredients of reality, stretching across every point in the universe without gaps or edges. Before there were particles, before there was light or matter, there were fields. They exist even in what we call a perfect vacuum, a permanent, silent presence underlying everything. In this view, solidity is an illusion. What we perceive as a particle, like an electron, is not a tiny, hard ball. It is better understood as a localized knot of energy, a tiny vibration or ripple within a much larger, unseen medium, the electron field. Every type of fundamental particle has its own corresponding field. There is an up quark field, a down quark field, a photon field. The entire universe is a symphony of these overlapping, intermingling fields, each with its own properties and rules. The shift in thinking is profound. We are not separate objects moving through empty space. We are intricate patterns of excitation, temporary disturbances in ancient, omnipresent fields. Your body, the device you are using, the air you breathe, all of it is just a complex dance of ripples on this cosmic ocean. This is why the quantum vacuum is never truly empty. Even when no particles are present, the fields themselves are still there, humming with potential. Understanding this is the key that unlocks the mystery of mass. Because if particles are just excitations, then a crucial question arises. Why are some ripples, like those for electrons and quarks, heavy and sluggish, while others, like the ripple for light, the photon, are massless and zip across the cosmos at the ultimate speed limit? The answer lies not with the particles themselves, but with the environment they move through. It requires a special kind of field, one that interacts with other fields in a unique way, turning some ripples from fleeting vibrations into something with substance. This is where our story finds its central character, the field that gives the universe its weight. This created a profound theoretical crisis, a crack in the very foundation of our understanding. For decades, physicists had been building the Standard Model, a magnificent mathematical framework that describes all known particles and 3 of the 4 fundamental forces. It was a masterpiece of prediction, its equations beautifully elegant, but this elegance came with a strict, non-negotiable condition. The equations governing the forces, specifically the weak nuclear force responsible for processes like radioactive decay, only worked if the particles carrying that force were completely massless. These particles are called the W and Z bosons. According to the pristine math, they should be like photons, the particles of light, zipping through the universe at the speed of light. There was just one enormous problem. Experiments proved definitively that the W and Z bosons are not massless. They are, in fact, incredibly heavy for fundamental particles, nearly 100 times the mass of a proton. The math said they must be weightless. Reality stubbornly insisted they were not. This was not a small discrepancy. It was a direct contradiction that threatened to unravel the entire theoretical structure. If the bosons had mass, the beautiful symmetry of the equations broke, and the theory's predictions fell apart. It was as if the blueprint for a perfect bridge explicitly forbade the use of support beams, yet the actual, standing bridge was held up by massive beams you could see and touch. The theory and reality were in open conflict. The same puzzling question applied to the building blocks of matter. Why does an electron have a specific, tiny mass? Why does a top quark have a colossal mass, while an up quark is almost feather-light by comparison? In the Standard Model's original formulation, these values were not explained. They were simply arbitrary numbers plugged into the equations, like unexplained constants of nature. This was deeply unsatisfying. Mass, the property that gives objects inertia and weight, the quality that makes the universe substantial rather than just ethereal light, could not be taken for granted. It was not a fundamental property handed to particles at their creation. It was something they had to acquire, a role they had to step into. But from where? What cosmic mechanism could grant mass to some particles while leaving others, like the photon, untouched, all without destroying the delicate mathematical harmony that made the theory work in the first place? Solving this crisis required a radical idea, one that proposed a hidden interaction between particles and an invisible presence filling all of space. The answer would not be found by changing the particles, but by changing the very stage upon which they performed. The elegance of the universe, it seems, is written in a language of symmetry. For physicists, symmetry is far more than a pleasing visual balance. It is a profound statement that the laws of nature remain unchanged under a transformation. Think of a perfect, featureless sphere. Rotate it any amount and it looks exactly the same. That rotational symmetry tells you something fundamental about the sphere's nature. In the quantum realm, the symmetries are more abstract, governing how fields interact with each other. The Standard Model is built upon a specific and powerful type called gauge symmetry. This is the mathematical engine that generates the forces themselves. It is a rule that says the equations describing a particle must stay the same even if we change how we measure its quantum properties at every point in space, in a smoothly coordinated way. This requirement is not arbitrary. It is a stringent demand for consistency, and from this demand, the very existence of force particles like the photon emerges naturally. The mathematics is breathtakingly beautiful. Gauge symmetry weaves the electromagnetic, weak, and strong forces into a single, coherent tapestry. But this beauty comes with a strict, non-negotiable condition. For the symmetry to remain perfect and unbroken, the particles that carry these forces must be massless. A massless particle, like the photon, can travel at the speed of light and does not resist acceleration. It is a perfect messenger, an ethereal carrier of influence. In this pristine mathematical world, the W and Z bosons of the weak force would be just like photons, weightless and swift. This was the theoretical ideal, a universe of perfect, weightless forces. Reality, however, presented a stubborn contradiction. Experiments showed the W and Z bosons were not only massive, but remarkably heavy. The beautiful, symmetrical equations described a universe that could not possibly be our own. It was a crisis of elegance. The very feature that made the theory so powerful and predictive also rendered it incapable of describing the world we actually inhabit. The symmetry had to be preserved because it was the source of the theory's predictive power, but the particles clearly had mass. The solution could not be to abandon the symmetry. Instead, physicists had to find a way for the symmetry to be both present and hidden. They needed a mechanism where the laws of physics themselves remain symmetrical, but the state of the universe we experience does not. This subtle but monumental idea is called spontaneous symmetry breaking. It is the process by which a perfectly symmetrical situation gives rise to an asymmetrical result. A simple analogy is a pencil balanced perfectly on its tip. The situation is completely symmetrical, every direction is equally valid, but the pencil cannot stay that way. It must fall, choosing one particular direction. The symmetry of the initial condition is broken by the final, stable state. The challenge was to apply this concept to the quantum fields filling all of space, to find a cosmic pencil that had tipped, giving mass to particles while keeping the underlying symmetrical laws intact. The search for that tipping point would lead to one of the most famous ideas in all of modern science. The answer to this cosmic standoff arrived not from modifying the known players, but by introducing an entirely new one into the arena. To preserve the beautiful symmetry of the laws while explaining the heavy reality we see, physicists proposed the existence of a new, all-pervasive quantum field. This is the Higgs field. It is not like the electron or photon fields, which are quiet and still in their lowest energy state, waiting to be excited. The Higgs field is fundamentally different. From the moment the universe began its current stable phase, this field has possessed a non-zero value everywhere, even in what we call a perfect vacuum. Think of it not as a silent stage, but as a stage that is always, uniformly filled with a faint, inescapable hum. This isn't a vibration or a ripple you can turn off. It is a permanent feature of empty space itself, a background value that is simply always on. This constant hum, this so-called vacuum expectation value, is the key to everything. It transforms the nature of empty space from a frictionless void into something with a subtle, universal texture. In this new picture, the universe is not filled with empty boxes. It is filled with this uniform, invisible presence, and this presence interacts with other fields in a very specific way. Some particles, like the photon, glide through this cosmic hum completely unaffected, remaining massless and moving at the speed of light. But other particles, like the W and Z bosons, and the fundamental matter particles like electrons and quarks, interact with this omnipresent Higgs field. That interaction is what we experience as mass. The stronger the interaction, the more resistance a particle feels as it tries to accelerate through this cosmic medium, and the heavier it becomes. It is less like a particle having an intrinsic weight, and more like it is moving through an invisible, universal molasses. Some particles are barely slowed by it, while others, like the top quark, are practically slogging through it, hence their tremendous mass. This single, elegant idea resolved the crisis. The underlying laws of the weak force remain perfectly symmetrical, just as the mathematics demands. But because the Higgs field has settled into its everywhere-on state, the symmetry of the universe we experience is spontaneously broken. The W and Z bosons are not born heavy. They acquire their mass by constantly plowing through this invisible field that fills all of space. The pencil has fallen, not by breaking a law, but by finding a stable state in a field-filled cosmos. So mass is not an innate property handed down at creation. It is an emergent phenomenon, a relationship between a particle and the silent, humming field that permeates the void. But a field you cannot see or feel proposed to solve a mathematical problem is one thing. Proving it physically exists is an entirely different challenge, one that would require the most ambitious machine ever built by humankind. So the Higgs field is this constant, humming presence everywhere. But how exactly does its mere existence translate into the solid weight of matter? The process is known as the Higgs mechanism, and it redefines what we mean by mass. Mass, in this view, is not something a particle inherently possesses. It is something that happens to a particle as it moves through the cosmos. Think of the universe not as empty space, but as a grand, endless ballroom that is uniformly packed with people. This crowd represents the Higgs field, present at every single point. Now, imagine two different individuals trying to cross this room. The first is an unknown guest, dressed plainly. They can slip through the crowd with relative ease, moving quickly from one side to the other without causing much of a stir. This particle experiences very little resistance. It has a very small mass. The second individual is a major celebrity. The moment they step into the room, the crowd reacts. People turn, they gather, they want to interact. The celebrity's progress across the floor becomes a slow, difficult slog. They are constantly engaged, surrounded, and slowed down by the sheer number of interactions. This particle experiences tremendous resistance. It has a large mass. In this analogy, the celebrity's fame is not their mass. Their mass is the difficulty of their passage, which is a direct result of how the crowd, the Higgs field, interacts with them. This is the essence of the mechanism. Every fundamental particle has a specific coupling strength, a sort of innate popularity with the Higgs field. A photon, the particle of light, has zero coupling. It is utterly invisible to the crowd. It glides through the universal ballroom completely unhindered, which is why it has no mass and travels at the ultimate speed. The W and Z bosons, however, have a very strong coupling. They are the ultimate celebrities of the quantum world to this particular field. Their journey is constantly impeded, which manifests as their significant mass. Electrons and quarks have their own unique coupling strengths, which is why they have the specific masses we measure. The electron interacts only modestly, giving it its light weight, while the top quark interacts so fiercely it becomes one of the heaviest known particles. This elegant process solves the symmetry crisis perfectly. The laws of physics remain symmetrical, like the uniform rules of the ballroom. But because the Higgs field has a non-zero value everywhere, the crowd is always present. The state of the universe is asymmetrical, and particles moving through it acquire their masses based on how they are received. We are all, at our most fundamental level, just patterns moving through this silent, cosmic crowd, our very substance granted by the difficulty of our passage. Yet for decades, this remained a brilliant but unproven mathematical idea. To move from theory to established fact, science needed to find a way to make the invisible field reveal itself. That proof would require creating a tiny, violent piece of the early universe right here on Earth. The critical moment of this cosmic tipping point is known as spontaneous symmetry breaking. To visualize it, picture not a pencil, but something far more fitting for the Higgs field itself. Imagine a shape like a sombrero or the rounded base of a wine bottle. The center rises to a peak, while the lowest points form a circular valley all around the rim. This shape represents the potential energy of the Higgs field. The peak at the very center is a high-energy, perfectly symmetrical state. Every direction outward is identical. In the earliest, hottest instance after the Big Bang, the universe was in this exact condition. The Higgs field sat at that unstable peak, its value at zero everywhere. In that state, all particles were massless, and the forces were unified in perfect, symmetrical harmony. But such a state is inherently unstable, like that pencil balanced on its tip. It cannot last. As the universe expanded and cooled, it lost energy. The Higgs field, like a marble placed at the peak of that hat, had to roll down into a state of lower, stable energy. It could not stay at the symmetrical center. It had to choose a direction, and so it fell randomly into the circular trough that surrounds the peak. That is the moment symmetry was spontaneously broken. The field settled into a stable, non-zero value that now fills all of space. But here is the profound consequence. Once it fell into that trough, it could not simply roll back up to the peak. The energy required was too great. The properties of the universe were frozen in place. The specific, non-zero value the field adopted became a permanent feature of the vacuum, an invisible constant against which all particles would now move. This single random event determined the coupling strengths, which in turn set the masses for every electron, every quark, every W and Z boson. It chose, from an infinity of possibilities, the specific rulebook for our reality. The symmetry of the laws remains hidden beneath the surface, but the state of our universe is irrevocably asymmetrical because of that ancient fall. We live in the aftermath of that cooling, in the trough of the cosmic wine bottle. The mass of everything you see, including yourself, is a direct relic of that one instant when the universe chose a direction and became substantial. But a theoretical shape and a historical event are one thing. To confirm this was not just a beautiful story, science needed to find physical evidence. It needed to detect the signature of the field itself, a ripple in its fabric. This meant finding the particle associated with it, the Higgs boson. The hunt was on to create the conditions of the early universe once more, to briefly lift the field back toward that peak and watch it fall. That cosmic tipping point left its signature everywhere, in the very mass of our atoms. But to confirm this monumental idea, scientists needed to see the field itself vibrate. Every quantum field has a corresponding particle, a ripple in its fabric. The electromagnetic field has the photon. The Higgs field, therefore, must have its own particle, the Higgs boson. This particle is not the field. It is a fleeting, localized knot of energy within it, a tiny splash in that universal, humming ocean. Detecting this splash would be the ultimate proof that the field was real, and not just a mathematical convenience. The challenge was staggering. To create a Higgs boson, you need to inject an enormous amount of concentrated energy into the vacuum, to briefly jostle the Higgs field out of its calm, stable state, and make it ring like a bell. You need to recreate, for a split second, the searing energy conditions that existed just after the Big Bang. This was the monumental task of the Large Hadron Collider. Buried deep beneath the border of France and Switzerland, this machine is a 27-kilometer ring of supercooled magnets. It accelerates two beams of protons to within a whisper of the speed of light, and then smashes them together head-on. In these collisions, the immense kinetic energy is converted into matter, following Einstein's famous equation. For a fleeting moment, smaller than a billionth of a second, the energy at the collision point becomes so intense that it can excite the Higgs field, plucking it to create a single, unstable Higgs boson. The particle itself lives for too short a time to ever be seen directly. It immediately decays into a shower of other, more familiar particles that spray out from the collision point. The hunt was not for the boson itself, but for the specific, predicted pattern of debris it would leave behind. It was like trying to prove a specific type of bell existed by listening for the unique echo it produced after being struck. in a room filled with the deafening noise of thousands of other bells ringing simultaneously. After decades of planning and years of collecting data from trillions upon trillions of collisions, the announcement came in July of 2012. The detectors had seen the telltale pattern. A new particle, consistent with the Higgs boson, had been observed. This was not just the discovery of another particle. It was the discovery of a fingerprint. That specific ripple in the data was evidence of the field that filled the stage. The invisible scaffold that keeps our universe from disintegrating had finally made its presence known. The discovery of the Higgs boson was a triumph, a direct glimpse of the cosmic scaffold. But to truly appreciate its silent work, we must ask what would happen if it were suddenly removed. Strip away the Higgs field, set its value back to zero, and the universe as we know it would not just change, it would instantly and utterly dissolve. First, mass itself would vanish. Every particle that interacts with the field would become weightless. Electrons, quarks, the W and Z bosons, all would shed their inertia like a heavy coat. And in the rules of relativity, a particle with zero mass has no other option. It must travel at the speed of light, the universe's ultimate speed limit. In this strange new reality, the electron orbiting an atomic nucleus would not be a bound particle in a stable cloud. It would be a flash of light, moving too fast to be captured by the proton's electric pull. Atoms could not form. The very concept of an element of hydrogen or carbon or iron would be meaningless. There would be no periodic table, because there would be nothing periodic to arrange. The consequences ripple outward into the forces that shape reality. In our universe, the W and Z bosons are massive, which severely limits their range. The weak nuclear force they carry only works over a subatomic distance, which is why it can orchestrate processes like nuclear fusion inside stars without disrupting larger structures. Without mass, these bosons would become long-range messengers, just like the photon. The weak force would stretch across light years, its influence no longer confined. Nuclear processes would run amok, destabilizing any potential clump of energy instantly. The delicate balance that allows atomic nuclei to exist at all would be shattered. The result is not a universe of new possibilities, but a universe of impossible chaos. No atoms means no molecules. No molecules means no chemistry. No chemistry means no solids, no liquids, no planets, and no stars. The cosmos would be reduced to a thin, uniform soup of massless particles and unconfined forces. A blinding sea of light-speed energy with no pockets of stability, no islands of complexity. Every structure, from a single proton to a grand spiral galaxy, relies on the resistance provided by mass, on the friction of moving through that invisible field. Without that friction, there is no grip for gravity to take hold, no way for anything to clump together. The universe would be a featureless, eternal flash, incapable of holding a memory, a pattern, or a thought. So when we say the Higgs field keeps the universe from disintegrating, it is not a poetic exaggeration. It is a literal, physical fact. The stability of your own body, the solidity of the ground beneath you, the very existence of time as a narrative rather than a single blinding instant, all are gifts of that ancient, silent hum. Our substantial world is a delicate miracle, suspended in the trough of a cosmic shape, held together by a field whose only direct signature was a tiny, fleeting ripple in a detector. Yet this triumphant discovery revealed a deeper, more unsettling mystery. The measured mass of the Higgs boson itself, while giving particles their weight, presents a number that threatens to unravel our elegant picture from within. This is known as the hierarchy problem, and it is one of the most profound cracks in the foundation of modern physics. To understand it, we must look at the scales involved. On one end, we have the familiar world of atoms and forces, governed by the Electroweak scale. This is the energy realm where the Higgs field operates, giving us the masses we see. It is a tiny, delicate number. On the other end of the cosmic spectrum lies the Planck scale, the unimaginably high energy domain where quantum gravity is believed to take over. This is the scale of the Big Bang's first moments of black hole singularities, where the very fabric of spacetime becomes a chaotic quantum foam. The difference between these two numbers is not just large. It is ludicrous. The Planck scale is about 100 million billion times larger than the Electroweak scale. It is the difference between the weight of a single proton and the mass of an entire planet. In a sensible universe, we would expect these vastly separated scales to remain separate. But quantum mechanics refuses to cooperate. Remember the seething quantum vacuum, that bubbling sea of virtual particles. According to the rules, every type of virtual particle that can interact with the Higgs field should contribute a little push or pull to its energy, and therefore to the mass of the Higgs boson. The heaviest particles, like the top quark, should contribute the most. When you add up all these infinite quantum corrections from every possible particle, the calculation suggests the Higgs mass should be violently yanked up to the Planck scale. It should be astronomically, incomprehensibly heavy, but it is not. The Higgs boson we found is incredibly light, sitting precisely in that delicate low-energy realm where it needs to be for our universe to exist. This creates a paradox of fine-tuning so extreme it strains belief. For the Higgs mass to end up so small, the raw, gigantic contributions from the Planck scale and the virtual particles must cancel each other out with a precision of more than 1 part in a million billion. It would be like balancing a pencil on its tip for billions of years, not through any supporting structure, but because two opposing hurricanes are blowing on it with exactly equal, unimaginable force, down to the last atom of air. Such perfect, unnatural cancellation seems absurd. It suggests our current understanding is incomplete, that something is missing from the equations. Physicists see this not as a failure, but as a blazing clue. The universe is hinting at a hidden layer of reality, new physics that naturally stabilizes this precarious balance. Leading ideas include supersymmetry, a theory proposing every known particle has a heavier, unseen twin, whose quantum contributions would neatly cancel out the problematic corrections. Others speculate about extraspatial dimensions curled up at tiny scales, changing how gravity and the other forces interact. The hierarchy problem tells us that the invisible field holding reality together may itself be held in place by principles we have yet to discover. The scaffold has been found, but now we must ask, what is supporting the scaffold? This precarious balance leads us to a startling, almost cinematic possibility. Based on the precise numbers we have measured for the Higgs boson and the top quark, some physicists have calculated that our universe might not be sitting in the true, absolute bottom of the cosmic wine bottle. Instead, we could be resting in a shallower dip on its side, a temporarily stable but ultimately precarious ledge. This is the concept of the false vacuum. In this view, the Higgs field in our region of space has a certain value that gives us the laws of physics we know. But mathematics suggests there could be a much deeper valley, a state of far lower energy that the field could fall into if given a big enough push. Our entire cosmos would then exist in a state of metastability. It is stable for now, but not forever. It is a cosmic accident waiting to correct itself. The mechanism for this correction is as elegant as it is terrifying, a process called quantum tunneling. Normally, for the Higgs field to roll from our false valley into the true, deeper one, it would need to climb over an immense energy barrier, like a ball needing a huge push to get over a hill. But in the quantum world, particles and fields can sometimes cheat. There is a tiny, non-zero probability that the field could simply appear on the other side of that barrier without going over the top, like a ghost passing through a wall. If such a quantum tunneling event were to occur anywhere in the universe, it would create a microscopic bubble of true vacuum. The laws of physics inside this bubble would be radically different. Fundamental constants like the strength of forces or the mass of electrons could change instantly. More critically, this new state would have a powerful, irreversible effect. The walls of this bubble, the boundary between the old false vacuum and the new true one, would expand outward in all directions at the speed of light. As it expands, it would rewrite reality in its wake, converting the unstable old universe into the stable new one. Anything caught in its path would cease to exist as we understand it. Atoms, stars, galaxies, the very fabric of spacetime itself would be transformed according to new, unknown rules. The process would be both instantaneous and undetectable from within. One moment our universe exists, the next, an expanding wall of new physics traveling at light speed, has already erased everything in its path, leaving no time for thought, for light, or for warning. It is crucial to understand the timescales involved, as they are the only comfort this theory provides. The probability of such a tunneling event happening in any given region of space in any given year is astronomically small. Calculations suggest the average time you would have to wait for it to occur is longer than a googol years, a number with more zeros than there are particles in the observable universe. Our cosmos is likely many, many orders of magnitude away from any such spontaneous transition. This is not an imminent threat, but a profound philosophical revelation about the nature of our existence. It paints our stable universe not as an eternal given, but as a beautiful, temporary island in a landscape of potential energies. The very field that grants us substance and stability might also contain the seed of our ultimate transformation. A reminder that the laws we consider fixed are perhaps just a local ordinance, not a universal decree. This leads us to wonder if our entire cosmic story, from the first particles to the last stars, is playing out on borrowed time, within a bubble of delicate physics that one day, in the unfathomably distant future, may simply pop. This concept of a false vacuum hints at a field with immense latent power, a power that may have already reshaped the cosmos in its infancy. To understand the universe we see today, we must travel back to its first incomprehensible moments, where the Higgs field, or something very much like it, may have played the most dramatic role of all. Cosmologists face a puzzle when they look at the large-scale structure of the universe. It is remarkably uniform. The cosmic microwave background, the ancient afterglow of the Big Bang, shows a nearly identical temperature in every direction we look. Yet, according to the original Big Bang model, these distant regions should never have been in contact to equalize their temperature. It is as if a room instantly reached a perfectly even warmth without any mixing of air. The leading solution to this and other cosmic riddles is a theory called inflation. It proposes that a fraction of a second after the beginning, the universe underwent a period of staggeringly rapid, exponential expansion. In an interval so brief it defies analogy, the fabric of space itself stretched faster than the speed of light, smoothing out any wrinkles, flattening the overall geometry, and magnifying quantum fluctuations into the seeds for all future structure. But what could possibly fuel such an explosive event? The engine needed for inflation is a special kind of field, one temporarily trapped in a high-energy state. As this field slowly rolls down its energy hill toward a stable minimum, it releases energy that drives the exponential expansion of space. The name given to this hypothetical field is the inflaton. And here, the properties of the Higgs field offer a compelling parallel. We already know the Higgs field underwent a dramatic transition, rolling from a high-energy, symmetrical state into the stable trough we inhabit today. Could the Higgs field itself have been the inflaton, or perhaps a close cousin, another scalar field with similar properties acting in those first moments? The idea is profoundly elegant. The same kind of cosmic mechanism that later gave particles their mass could have first been responsible for shaping the entire arena in which those particles would exist. In this scenario, the early universe was in a state of false vacuum, with the inflaton field perched high on its energy hill. This high energy density acted like a repulsive force, causing space to expand at a fantastic rate. As the field eventually began its slow roll downward, that inflationary period ended, and the pent-up energy was released as a hot soup of particles, what we traditionally call the Big Bang fireball. The tiny quantum jitters present in that field during inflation were stretched across the cosmos, becoming slight variations in density. These are the seeds gravity would later nurture into galaxies, stars, and planets. So the very field that prevents disintegration may have also been the sculptor, taking a chaotic, microscopic speck and inflating it into a vast, smooth, and fertile cosmos. The connection remains theoretical, a tantalizing link between the physics of the unimaginably small and the destiny of the impossibly large. It suggests that the silent hum we now detect is an echo of the universe's first and most creative breath, a force that built the stage before assigning the actors their roles. But the discovery of the Higgs boson was not an ending. It was a doorway. The properties we measured for this particle are so precise, and yet so strangely balanced, that they point toward something deeper. The Higgs field, in its current form within the Standard Model, feels like a final piece of a puzzle that is itself sitting on a much larger table. Many physicists believe it is not a solitary actor, but a clue to a grander, hidden structure. This has launched the search for what lies beyond the Standard Model, where the humble Higgs might be the key to unlocking the universe's darkest secrets. One of the most elegant ideas is supersymmetry. This theory proposes a profound and beautiful symmetry between the two fundamental classes of particles: the fermions, like electrons and quarks that make up matter, and the bosons, like photons and gluons that carry forces. Supersymmetry suggests that for every known particle, there exists a hidden superpartner. The electron would have a selectron, the quark would have a squark, the photon would have a photino. These partner particles would have different quantum properties, most notably a different spin. If this symmetry were perfect, these twins would have the same mass as their ordinary counterparts, and we would have seen them long ago. The fact that we have not tells us that if supersymmetry exists, it is a broken symmetry. The superpartners must be much heavier, hiding from our current colliders. And here is where it connects to our cosmic scaffold. The heavy superpartners, through their virtual quantum dances, would naturally cancel out the gigantic contributions to the Higgs mass from particles like the top quark. They would solve the hierarchy problem with elegance, stabilizing the Higgs field without any unnatural fine-tuning. The universe's precarious balance would be explained by a hidden, symmetrical mirror world. While we have not yet found any direct evidence for these superpartners, their theoretical elegance keeps them a compelling guidepost for future discovery. Another radical possibility reimagines the Higgs boson itself. What if it is not fundamental? In the composite Higgs model, the Higgs boson is not a ripple in a basic field, but a bound state, a kind of particle composite made of other, more fundamental constituents, held together by a new, ultra-strong force. Think of it like a proton. We once thought the proton was fundamental, but we now know it is made of quarks held by the strong nuclear force. In this view, the Higgs could be similar, a composite object emerging from a deeper layer of reality. Its lightness would then be natural, a consequence of its structure rather than a miraculous cancellation. This idea turns the Higgs from a fundamental field into a symptom of a much richer, more complex quantum world operating at energies we have yet to probe. Perhaps the most tantalizing connection is to the universe's greatest mystery, dark matter. We know dark matter exists because of its gravitational pull on galaxies, but we have no idea what it is made of. Could the Higgs field be the bridge? Some theories propose that dark matter particles interact with ordinary matter almost exclusively through the Higgs field. They would feel the same cosmic molasses that gives us mass, but they would be invisible to the forces of light and electricity. In this scenario, the Higgs is not just the giver of mass for our visible world, but also the sole communicator with a vast, hidden realm that makes up most of the matter in the cosmos. It becomes a universal translator between the seen and the unseen. Finally, the Higgs might be connected to other hidden fields. Some models suggest our universe is filled with multiple scalar fields, like the Higgs, each with its own role. One might have driven cosmic inflation. Another might govern the strength of dark energy. The Higgs could be just one voice in a chorus of invisible fields that collectively orchestrate the evolution and structure of everything. Each of these paths turns the Higgs from an answer into a question, a portal to new physics. Its precise measurements are not just confirming what we know, they are a map pointing to where our current knowledge ends. The field that holds reality together may be the very thread we pull to unravel the next layer of the cosmic mystery, leading us toward a fuller understanding of where the scaffold itself came from, and what other structures it might be supporting in the dark. Theoretical elegance is one thing, but the universe demands proof. Validating a 50-year-old idea required an experiment on a scale humanity had never before attempted. The Large Hadron Collider was built for one primary purpose: to recreate, for a fleeting instant, the unimaginable energies that existed just after the Big Bang. By accelerating protons to within a hair's breadth of light speed and smashing them together, scientists could conjure a microscopic fireball of pure energy, a window back to the universe's first trillionth of a second. Within that maelstrom, the hope was to excite the silent Higgs field, making it ring like a bell and produce its signature particle. But finding that one specific ripple in the quantum ocean was a task of staggering difficulty. The Higgs boson, if it existed, would be unstable, vanishing in a fraction of a moment. It could not be observed directly. Instead, physicists had to search for the unique shower of secondary particles it would decay into, a specific fingerprint hidden within an avalanche of debris from trillions of other, more common collisions. This was the monumental task of the detectors, ATLAS and CMS, cathedral-sized machines wrapped around the collision points. They are layered, digital ecosystems designed to track and identify every fragment of matter and energy that sprays out from the heart of a collision. Their sensors, working in perfect synchrony, had to distinguish the faint, predicted signal of a Higgs decay from an endless cosmic background noise. It was a search for a whisper in a hurricane. For years, the collider produced mountains of data, analyzed by thousands of researchers worldwide. They were looking for a statistical bump, a slight excess of events matching the predicted decay patterns over what random chance would allow. The tension built across the global physics community. Then, in July of 2012, the announcement came. In a packed auditorium at CERN, the leaders of the ATLAS and CMS collaborations presented their results. Both independent detectors had seen the same signal: a new particle with a mass around 125 gigaelectronvolts. The evidence met the gold standard of discovery in physics, a 5 sigma significance, meaning there was only a 1 in 3.5 million chance the signal was a random fluke. The room erupted. A theoretical prediction made half a century earlier had been confirmed. The Higgs boson was real. This was more than just the discovery of another particle. It was the validation of an entire mechanism for how the universe works. The invisible field, the cosmic molasses that gives particles their mass, was no longer a beautiful idea. It was a feature of our reality. The final piece of the standard model had clicked into place, completing our most successful map of the fundamental world. Yet, in that moment of triumph, a new chapter of questions immediately began. Yet this profound success reveals a paradox of staggering proportions. The very field that grants stability to matter also contributes to the energy of empty space itself. And here our equations produce a number so catastrophically wrong it threatens to unravel our entire understanding of the cosmos. This is the vacuum catastrophe, and it centers on a deceptively simple question: how much energy does nothing contain? According to quantum field theory, the vacuum is not nothing. It is a simmering sea of quantum fluctuations, with every field, including the Higgs, contributing a baseline energy. The Higgs field, with its constant, non-zero value everywhere, is a major player in this. Its contribution to the energy density of the vacuum can be calculated, and the result is not just large, it is monstrous. The theoretical prediction for the vacuum energy from all known fields, dominated by the Higgs, is over 120 orders of magnitude larger than the value we actually observe for dark energy. To grasp the absurd scale of this error, consider a single grain of sand. The difference between the predicted vacuum energy and the observed dark energy is like comparing that single grain to the entire observable universe, and then multiplying that mismatch by a factor of a trillion trillion trillion. It is the worst prediction in the history of science. This is the vacuum catastrophe. Our most successful theory of the small-scale world gives us an answer for the energy of empty space that is impossibly, uselessly huge. Yet when we look out at the large-scale universe, we measure the effects of vacuum energy, what we call dark energy, and it is incredibly, delicately small. This dark energy is causing the expansion of the universe to accelerate, a discovery that earned a Nobel Prize, but its measured value is a whisper compared to the theoretical scream. This means one of two things. Either our understanding of quantum fields and the vacuum is missing a crucial piece of physics that cancels out this enormous energy with near-perfect precision, leaving behind only the tiny residue we see as dark energy, or dark energy is something entirely different, unrelated to the quantum vacuum we understand. Both possibilities are humbling. The first suggests a fine-tuning so exquisite it defies belief, as if the universe's energy budget were balanced on a knife's edge by unseen forces. The second suggests we are fundamentally misunderstanding the nature of empty space. The Higgs field solved one existential crisis by giving us mass, but in doing so, it unveiled an even deeper one. It showed us that the energy cost of our stable reality is a number that, according to our best math, should have torn the universe apart before it could even form. That it did not is perhaps the greatest unsolved puzzle in fundamental physics, a silent warning that the scaffold holding us together is part of a structure whose full blueprint remains hidden in the dark. So the field is not a static backdrop, but a living, breathing presence. This constant hum has a texture, a granularity born from the quantum world. Even in its stable, lowest energy state, the Higgs field is never perfectly still. It experiences constant quantum fluctuations. These are not full-fledged Higgs bosons popping into existence, but something more subtle and pervasive. They are momentary, virtual distortions in the field itself, tiny ripples that borrow energy from the vacuum for a fleeting instant before vanishing back into the quiet hum. Think of a calm pond on a windless day. Its surface appears perfectly flat and smooth. But if you look closely at the molecular level, you would see constant, tiny vibrations as water molecules jostle against each other. The Higgs field is like that. Its overall value is constant, providing the universal molasses, but at every single point, it is fizzing with these imperceptible quantum jitters. These are virtual Higgs particles, ghostly echoes of the real thing that exist only as a temporary possibility within the seething quantum foam. And these ghosts have a real, tangible effect. They are part of the invisible background noise of reality that influences how other particles behave. When an electron moves through space, it is not just interacting with the average, smooth value of the Higgs field. It is also constantly brushing up against these fleeting virtual fluctuations. This interaction slightly alters the electron's properties, including its mass and how it scatters off other particles. These effects are incredibly tiny, but in the precise world of particle physics, they are absolutely essential. To make predictions that match the stunning accuracy of experiments at places like the Large Hadron Collider, physicists must account for every single quantum contribution, including these virtual Higgs fluctuations. They are calculated using intricate diagrams called Feynman diagrams, where virtual particles appear as internal lines, representing the short-lived quantum handshakes that facilitate every interaction. The fact that these calculations, which include the dance of virtual Higgs particles, produce predictions that match experimental data to many decimal places is powerful confirmation. It tells us the Higgs field is not just a passive stage. It is a dynamically active participant in every quantum event. Its silent hum punctuated by an endless storm of virtual activity. This means that what we call empty space is far from inert. It is a vibrant quantum plenum, where the field that grants mass is itself in a state of perpetual, invisible agitation. The scaffold is not just holding things up, it is subtly vibrating, and those vibrations are woven into the very fabric of every interaction, every collision, and every stable atom in the cosmos. The history of the Higgs field is written in the cooling of the cosmos itself. To understand its journey, we must rewind time to the universe's first, unimaginably hot moments. In that primordial inferno, temperatures were so high that thermal energy thrummed through every point in space. This intense heat dominated the cosmos, preventing any field from settling down. The Higgs field in this environment was held at bay. Its value was pinned at zero everywhere. This was the symmetric phase, a brief period of perfect, weightless unity. In this state, the laws of physics displayed their full, elegant symmetry. The electromagnetic and weak forces were not separate entities, but one unified electroweak force. The W and Z bosons were massless, just like the photon, and all particles moved at the speed of light. Matter, as we know it, could not exist. It was a universe of pure, radiant energy, a formless and chaotic fire where no structure could take hold. This was not a stable state, but a temporary condition imposed by the sheer violence of the birth of everything. The universe was expanding and cooling at a phenomenal rate. With each passing fraction of a second, the average energy of particles dropped. The thermal jostling that had kept the Higgs field at its unstable zero point began to lose its grip. A critical threshold was approaching, a cosmic temperature akin to the freezing point of water. For the Higgs field, this was the moment of condensation. As the universe cooled below approximately 160 billion degrees Kelvin, the energy landscape fundamentally shifted. The central peak of the wine bottle shape became untenable. The field, everywhere at once, began its inevitable roll down the energy hill, seeking stability. It condensed into the circular valley, adopting a specific, non-zero value. This was the electroweak phase transition. The moment symmetry was spontaneously and permanently broken. The single electroweak force fractured into the distinct electromagnetic and weak forces we see today. The W and Z bosons, by interacting with the newly formed Higgs field condensate, suddenly became incredibly heavy, while the photon remained free. Quarks and electrons acquired their masses. The universe gained substance, friction, and the possibility of form. But a crucial question remains about how this transition unfolded. Did the Higgs field settle gently, like water smoothly turning to ice across a pond? Or did it change violently, like water flashing into steam? The difference hinges on the shape of that energy landscape. If the transition was smooth and continuous, it's known as a second-order phase transition. The field's value would have changed gradually as the universe cooled, a quiet cosmic shift. However, if there was an energy barrier, a hump between the high-temperature zero state and the low-energy valley, the story becomes more dramatic. In that case, the universe would have remained in the false, high-energy vacuum even as it cooled below the critical temperature. It would have been supercooled, trapped in a metastable state. Then, randomly, in bubbles scattered across space, quantum tunneling would have occurred. In these bubbles, the Higgs field would have suddenly jumped the barrier, flipping to its true, stable value. Each bubble would then expand at nearly the speed of light, colliding and merging with others until the entire cosmos was converted. This is a first-order phase transition, and it would have been a cataclysm of unimaginable scale. The collision of these expanding bubble walls would have released titanic amounts of energy, rippling the very fabric of spacetime itself. These ripples are gravitational waves, literal wrinkles in the continuum of space and time. If this violent transition occurred, a faint, primordial hum of these gravitational waves should still permeate the cosmos today, a fossilized echo of the moment the universe gained its mass. Our current data suggests the transition in the Standard Model was likely too smooth, too gentle to produce waves we could detect. But this is where new physics enters the stage. If the Higgs field is connected to something beyond the Standard Model, like supersymmetry, the energy landscape could be dramatically different. It could easily allow for a powerful first-order phase transition. This makes the hunt for these primordial gravitational waves one of the most exciting frontiers in cosmology. Upcoming observatories like the Space-Based Laser Interferometer Space Antenna or ground-based arrays are designed to listen for this specific frequency from the dawn of time. Finding that signal would do more than confirm a dramatic cosmic event. It would provide direct evidence that the Higgs field's awakening was a turbulent birth, and it would open a window into the physics that guided its fall, revealing the hidden architecture of reality's very first second. These analogies are vital tools for our intuition, but they each come with a crucial caveat. Take the celebrity in a crowded room. It wonderfully illustrates how a particle's interaction strength determines its effective mass, but it risks implying the field is made of other particles. The crowd is separate from the celebrity. In reality, the Higgs field is the stage itself, a uniform presence, and the particle is the disturbance moving through it. There is no separate crowd of Higgs bosons impeding progress. The field is the medium, not the obstruction. The molasses or cosmic syrup analogy is equally useful for conveying that space itself has a subtle texture. It correctly suggests that massless particles like photons feel no resistance, while others get bogged down. Yet this picture can mislead us into thinking the Higgs field exerts a drag force, like a fluid slowing a moving object. That is not quite right. Inertia is not about continuous slowing. It is the resistance to a change in motion. A more precise way to think of it is that the interaction with the field determines how much energy is required to accelerate a particle in the first place. The field gives particles their heft, their substance, not their speed. Perhaps one of the most clarifying analogies is that of a vast, uniform snowfield. Imagine two travelers crossing it. The first is on skis. They glide effortlessly across the surface, barely disturbing the snow beneath them. This is the photon, interacting so weakly with the Higgs field that it experiences no mass and moves at light speed. The second traveler wears heavy boots. With every step, they sink deeply into the snow, requiring great effort to lift their feet and move forward. This is the W or Z boson, interacting so strongly with the field that its progress is laborious. Its mass is the energy required to slog through that snow. This analogy helps separate the idea of the field, the snow, from the traveler's mode of transport, which represents the particle's inherent coupling strength. The core limitation of all these pictures, however, is a subtle but profound one. They are all spatial. They depict an object moving through a substance that fills space. The Higgs field, however, is not just in space. It is a component of spacetime itself, a fundamental property of the vacuum. A particle does not enter the field when it moves from point A to point B. The field is already at point A, point B, and everywhere in between. The interaction is constant and instantaneous, not something that happens upon contact. The field confers mass as an intrinsic property of a particle's existence, not as a consequence of its travel. This is why, in the equations, mass is a constant, not a variable that changes with velocity within the field. Grasping this distinction protects us from a common misconception. The Higgs mechanism does not mean empty space is sticky or viscous. If that were true, even massless photons would eventually lose energy, and the universe would slowly grind to a halt. Instead, the field's uniform value simply changes the rules of the game for certain particles, altering how they respond to forces. It rewrites their very nature. So while we lean on these everyday comparisons to build understanding, we must remember they are scaffolds for our imagination, not the final structure. They point toward a truth that is, at its heart, uniquely quantum, a silent negotiation between a ripple and an endless, humming ocean that defines what it means to be substantial at all. The precise tuning of the Higgs field forces us to confront a question that straddles the line between physics and philosophy. If the field's value, or the mass of the quarks it produces, were even slightly different, the story of our universe would be a short and tragic one. A few percent more, and protons would bind too tightly, preventing the formation of diverse atomic nuclei. A few percent less, and protons would not bind at all. In either scenario, the universe would be a boring place of hydrogen and helium, or a featureless soup of subatomic particles. The complex elements essential for planets, oceans, and living beings like carbon and oxygen would never be forged in the hearts of stars. The narrow window for this cosmic chemistry is astonishingly small. It suggests our existence hinges on a razor's edge of physical constants, a delicate balance that seems too perfect to be mere chance. This apparent fine-tuning for life is one of the most haunting mysteries in modern cosmology. Why does the universe seem so curiously hospitable? One compelling answer comes from the Anthropic principle, a simple but profound idea. It states that the universe we observe must be compatible with the existence of observers. We are here to ask the question, so we necessarily find ourselves in a universe with the right conditions for life. This is not an explanation in itself, but a logical filter. It shifts the question from why is the universe fine-tuned for life, to how can a universe fine-tuned for life come to exist? This is where the concept of a multiverse enters the stage. If our cosmos is just one bubble in an infinite, frothing sea of universes, each with its own random set of physical laws and constants, then the mystery dissolves into a matter of probability. In an infinite multiverse, every possible value for the Higgs field, every possible strength for gravity, every possible version of reality would play out somewhere. Most of those universes would be stillborn or barren, incapable of generating complexity. But a vanishingly small fraction, by pure statistical chance, would land on the magical numbers that allow stars, planets, and life to emerge. We, of course, find ourselves in one of those rare, habitable bubbles, simply because we could not exist anywhere else. The multiverse idea turns a miraculous coincidence into an inevitable selection effect. The scaffold of our reality is not a necessary truth, but a fortunate accident in an endless cosmic lottery. Yet for many scientists, this feels like a retreat from explanation. It trades one mystery for another, vastly larger one. The search continues for a deeper, more elegant answer. Perhaps there is an undiscovered physical principle, a law of nature we have not yet glimpsed, that uniquely determines the Higgs field's value and all other constants. Perhaps the numbers are not random, but the only possible solution to a grander, unified equation. The fine-tuning might be a clue, a fingerprint of a more fundamental theory where everything is connected, and life is not a bizarre accident, but a natural consequence of the universe's deepest logic. This philosophical weight rests on every measurement made at the Large Hadron Collider. Each new datum about the Higgs boson's behavior is a test, probing whether our universe is a lonely, finely tuned artifact, or one thread in a breathtakingly vast and varied cosmic tapestry. The field that gives us substance may also be the key that unlocks the ultimate nature of our existence, revealing whether we live in a necessary universe or a profoundly lucky one. The search for a cosmic field may seem like a purely abstract quest, but the tools built to find it have reshaped our world in tangible ways. Chasing the invisible scaffold of reality demanded engineering on a scale that pushed the very limits of human ingenuity, and the solutions invented for the Large Hadron Collider have rippled outward into society. To contain the proton beams racing around its 27-kilometer ring, scientists needed magnets of unprecedented power. Ordinary electromagnets would have been impossibly large and wasteful. The answer was superconductivity, the property where certain materials, when chilled to incredibly low temperatures, lose all electrical resistance. The LHC required over 1,200 massive dipole magnets, each using superconducting niobium titanium cables to bend those beams. To make them superconducting, the entire magnet system must be cooled to a staggering negative 271.3 degrees Celsius, just 1.9 degrees above absolute zero. This is colder than the void of deep space. Achieving this required a cryogenic system of breathtaking complexity, a distributed network pumping superfluid helium. The technological leaps made here have directly advanced medical imaging, where superconducting magnets are the heart of every modern MRI machine, allowing doctors to peer non-invasively into the human body with exquisite detail. The quest to see the Higgs boson also meant handling an ocean of data. The collisions at the LHC produce around 1 petabyte of raw data every single second, a volume that would fill over 200,000 DVDs. It is impossible to store it all, so a trigger system of advanced electronics and software makes a split-second decision on what 1/10,000th of that information is interesting enough to keep. The filtered data is then distributed globally for analysis via a computing grid, a concept pioneered at CERN. This very need to share complex information among scientists across continents was, in fact, the original catalyst for a now ubiquitous tool. In 1989, a researcher at CERN named Tim Berners-Lee proposed a system to link and share documents over the Internet. He called it the World Wide Web. What began as a tool for particle physicists to collaborate is now the foundational layer of our connected world. Even the detectors themselves have spurred innovation. The precise particle tracking developed for experiments like ATLAS has found application in improving the resolution of positron emission tomography, or PET scans, a vital tool in cancer diagnosis and treatment. This pattern is a profound lesson in how curiosity-driven science works. We set out to answer a fundamental question about the nature of the cosmos, and in building the machines to seek that answer, we are forced to invent new technologies, new materials, and new ways of thinking. These innovations then diffuse into the broader world, curing illnesses, connecting humanity, and creating industries that did not exist before. The Higgs field gives the universe its substance, but the hunt for it has given our civilization new tools to see, to heal, and to understand our own world more deeply. The monumental discovery of the Higgs boson sent ripples far beyond the world of physics, capturing the global imagination. Yet for many, the science was eclipsed by a single, powerful nickname, the God particle. This label, while undeniably evocative, tells a story of how complex ideas enter public consciousness and what can be lost in translation. The term did not originate from a scientific paper or a press release at CERN. It came from the title of a popular science book written by physicist Leon Lederman in the 1990s. Lederman, a Nobel laureate and a man with a well-known sense of humor, reportedly wanted to call it the Goddamn particle, out of sheer frustration over how elusive and difficult it was to detect. His publisher, understandably, suggested a more marketable alternative. The name stuck, instantly capturing headlines and public curiosity. It provided a shorthand for something profoundly important, a key to existence itself. For physicists, however, this nickname is often met with a collective wince. The discomfort is not about the word itself, but about the profound misunderstanding it can seed. Calling the Higgs the God particle suggests a singular, mystical origin point for all of creation, a divine spark that breathes substance into the void. This framing is deeply misleading. The Higgs mechanism is not a moment of creation, but a process of condensation. It is not a singular particle bestowing grace, but a ubiquitous field granting property. The field is a fundamental piece of nature's machinery, as integral to the cosmos as gravity or electromagnetism. Its discovery did not reveal a hand guiding the universe, but a rule written into its fabric. The misnomer risks turning a brilliant, testable piece of physics into a metaphor for something untestable and supernatural. It can make the field seem like an exception to the rules of nature, rather than their brilliant confirmation. In doing so, it subtly diminishes the actual achievement. The real wonder is not that something magical happened, but that something so elegantly mechanical and inevitable did. The universe cooled, a field settled into a stable state, and that simple act of finding equilibrium gave rise to everything we know. That story of cause and effect written in mathematics and confirmed by a colossal machine is in many ways more awe-inspiring than any mystical label. It tells us the universe is comprehensible, that its deepest secrets yield to curiosity, patience, and human ingenuity. The cultural embrace of the God particle nickname, however, highlights a beautiful tension. It shows a public hunger to connect with profound scientific truths, to find meaning in the architecture of reality. The challenge and the opportunity is to channel that hunger toward the richer, more nuanced truth. The Higgs field is not a deity. It is something perhaps more remarkable, a silent, universal participant in every atom of our being, a testament to the fact that we can uncover the hidden scripts of the cosmos and find our own substance written within them. Before the Higgs field solved the puzzle, physicists explored other, more radical possibilities. One compelling alternative was known as Technicolor. This theory proposed that mass did not come from a new, fundamental field at all. Instead, it suggested the existence of a brand new, ultra-strong force, similar to the strong nuclear force that binds quarks inside protons and neutrons. In this picture, particles like the W and Z bosons would gain their mass by being bound states, or composites, held together by this powerful new interaction. The theory borrowed its name from the strong force's property of color charge, envisioning a technological cousin, hence Technicolor. It was an elegant idea that avoided introducing a fundamental scalar field, which some physicists found philosophically unsatisfying. For a time, it was a serious contender, offering a different path to break Electroweak symmetry and give the universe its substance. Yet, as the standard model solidified through decades of precise experiments, the Higgs mechanism gradually emerged as the frontrunner. Its key advantage was mathematical necessity. The Higgs field, as a scalar field, fit into the existing equations with a natural elegance that preserved the gauge symmetry at the heart of the theory. It provided a minimal, self-consistent extension that did not require inventing an entirely new force with unseen particles. The Higgs framework made specific, testable predictions, not just for a new particle, but for its precise properties and how it would interact with others. Technicolor and other alternatives, while ingenious, struggled to match the same level of predictive precision without becoming overly complex. They could explain mass, but they often did so in ways that created more puzzles than they solved, or predicted phenomena that experiments failed to find. The decisive moment, of course, came from the Large Hadron Collider. The discovery of a new scalar particle with a mass around 125 gigaelectronvolts, interacting with other particles with strengths proportional to their mass, was the exact fingerprint predicted by the Higgs mechanism. It was a clean, direct confirmation that aligned perfectly with the decades-old mathematics. Technicolor, in its original form, did not predict such a particle. This experimental evidence closed the book on the long debate. The Higgs field was not just a clever idea, it was a feature of our reality. The search for the source of mass became a story of how one elegant solution, born from mathematical consistency, patiently waited for our technology to catch up and reveal its truth in the debris of a collision. The confirmation of the Higgs boson was not an ending, but a beginning. With its existence proven, the real detective work could start. The question is no longer if the field exists, but how it truly behaves. Every detail of its interaction is a clue to a larger reality. This marks a monumental shift from discovery to detailed exploration, and it demands a new generation of experiments. The primary tool for this next decade will be an upgraded version of the very machine that found it, the High-Luminosity Large Hadron Collider. Luminosity, in this context, is a measure of collision rate. Think of it like the resolution of a microscope. The initial discovery was like spotting a faint, blurry star in a vast night sky. The upgrade is about turning the most powerful telescope in the world directly toward that star, collecting vastly more of its light to see its color, its atmosphere, and any faint companions orbiting it. The High-Luminosity LHC will increase the number of proton collisions by a factor of 10. It will produce not just hundreds, but millions of Higgs bosons. This avalanche of data is essential because the most telling secrets are hidden in the rarest of events. One of the primary goals is to measure how the Higgs field interacts with itself. This is known as the Higgs self-coupling. Remember the shape of the cosmic wine bottle, the potential energy landscape. The mass of the Higgs boson tells us the curvature of the walls near the bottom of the valley we live in. But to map the entire shape, to understand the full energy potential of the field, we need to see how it interacts with itself. This is probed by searching for the extremely rare production of two Higgs bosons at once. Observing this process would allow physicists to measure the strength of the Higgs field's own self-interaction, directly testing our understanding of that cosmic landscape. It would tell us if the valley we reside in is shaped exactly as the standard model predicts, or if its contours hint at new physics, perhaps a connection to that deeper, true vacuum. Another critical search is for the Higgs boson decaying in unexpected ways. In the standard model, the Higgs decays into a set of known particles with very specific probabilities. But what if it occasionally decays into something invisible? This could be a direct portal to dark matter. If dark matter particles interact with ordinary matter solely through the Higgs field, then a Higgs boson might decay into a pair of these invisible particles, carrying away energy and momentum without leaving a trace in the detectors. Finding such an event, a Higgs boson that seems to vanish into nothing, would be one of the most dramatic discoveries imaginable, directly linking the field that gives us mass to the hidden substance that shapes the cosmos. Finally, precision will test the most fundamental prediction of the Higgs mechanism. The theory states that a particle's coupling to the Higgs field should be directly proportional to its mass. We have confirmed this beautifully for heavy particles like the top quark and the W boson. But what about the lighter ones? A crucial test involves the muon, a heavier cousin of the electron. The muon interacts very weakly with the Higgs because it is relatively light. Measuring this tiny coupling with extreme precision is like trying to hear a whisper in a quiet room. Any deviation from the predicted whisper, even the faintest hint of a different tone, would signal that something is missing from our equations. It could be evidence of undiscovered particles influencing the interaction, or a sign that the Higgs has hidden partners of its own. This meticulous work transforms the Higgs boson from a trophy on the shelf into a precision instrument. Each measurement is a dial on a cosmic control panel, and by reading them with ever greater accuracy, we are not just confirming what we know. We are listening for the subtle cracks in the theory, the faint signals that will guide us to whatever lies beyond the standard model, to the deeper architecture that supports the invisible scaffold of our reality. This invisible scaffold, while granting us stability today, may also hold the script for the universe's final act. The calculations of metastability of that precarious false vacuum are not static. They depend critically on the precise mass of the Higgs boson, and even more so on the mass of the top quark, the heaviest known particle. The latest measurements from the Large Hadron Collider have refined these numbers, allowing physicists to map the cosmic energy landscape with unprecedented accuracy. The result is a fascinating, if unsettling, portrait. Our universe almost certainly resides in a metastable state, but the energy barrier separating us from a deeper, true vacuum is astronomically high. The probability of a quantum tunneling event triggering vacuum decay in any given region of space over the entire age of our cosmos is so vanishingly small, it is effectively zero for all practical purposes. You would need to wait for a time so long it makes the lifetime of stars seem like a blink. A number with more zeros than there are atoms in billions of galaxies. From a human perspective, this is the ultimate reassurance. Our cosmic home is secure for timescales that dwarf any meaningful conception of the future. Yet, from a philosophical standpoint, the implication is profound. It means the laws of physics we consider eternal and fixed are, in principle, temporary. They are a local ordinance, not a universal decree. This ties the Higgs field directly into the grand narrative of cosmic fate. For over a century, cosmologists have pondered how the universe will end based on the behavior of dark energy. The leading scenarios have evocative names. In the heat death or big freeze, the universe expands forever. Stars burn out, black holes evaporate, and all energy gradients smooth into a featureless, lukewarm sea where nothing ever happens again. In the more dramatic Big Rip scenario, dark energy strengthens over time, eventually overcoming all forces, first tearing apart galaxies, then solar systems, then planets, and finally atoms and nuclei themselves. Both are stories told by the expansion of space, but the Higgs field introduces a third, far more abrupt possibility, a plot twist written into the vacuum itself. A vacuum collapse would not be a slow fading or a violent tearing. It would be a silent, instantaneous rewriting of reality from the inside out. If a bubble of true vacuum ever nucleated, it would expand at light speed, converting our universe into a new one with different physical laws. In that new state, the concept of a galaxy, a planet, or a thought might be as meaningless as a snowflake in a blast furnace. This speculative connection places the Higgs at the heart of both our origin and our potential end. Its dynamics in the first fractions of a second may have inflated the cosmos, and its latent instability may one day, in an epoch so distant it defies imagination, bring the curtain down. It is a reminder that the forces which build are also the forces which can transform. The search to understand this is not about forecasting doom, but about comprehending the full life cycle of physical law. By measuring the Higgs field's properties with ever greater precision, we are not just studying why we are here. We are reading the subtle clues in the cosmic foundation, clues that hint at whether our universe is a permanent edifice, or a beautiful, temporary structure in an even vaster and more mysterious landscape of possibility. The Higgs field, while solving one cosmic mystery, has opened a dozen more profound doors. Its discovery did not complete our picture of reality. Instead, it handed us a new and powerful lens, a set of precise clues pointing toward truths that lie just beyond our current understanding. The first and most pressing is the hierarchy problem, the staggering fine-tuning that keeps the Higgs boson so inexplicably light. This unnatural cancellation screams for an explanation, suggesting hidden particles or new symmetries like supersymmetry that naturally stabilize the scales of nature. Then there is the vacuum catastrophe, the embarrassing fact that the Higgs field's contribution to the energy of empty space is over 100 orders of magnitude larger than the dark energy we observe accelerating the cosmos. This is not a small error. It is a fundamental crisis, indicating we either misunderstand the quantum vacuum entirely, or a miraculous cancellation is hiding a deeper principle. We must also ask where the field's specific potential, the shape of its cosmic wine bottle, comes from. Why this particular valley depth and slope? The values seem arbitrary, yet they determine the masses of every particle and the stability of every atom. Are these numbers random, selected by chance in a vast multiverse? Or are they uniquely determined by a more fundamental theory we have yet to discover? The Higgs may also hold the key to our cosmic origin. Could it, or a field like it, have been the inflaton that drove the universe's explosive early growth? Finding a link between the Higgs and inflation would weave the story of mass creation directly into the story of space creation itself. And perhaps most fundamentally, is the Higgs field truly elementary? Or is it composite, a bound state of more basic constituents held by a new, ultra-strong force? A revelation that would revolutionize our view of what is fundamental. Each of these questions transforms the Higgs from an answer into a guide. Its measured properties are not just data points. They are signposts in an uncharted landscape. Every tiny deviation from prediction, every subtle interaction measured at the next generation of colliders, could be the first glimpse of that new terrain. The field that gives our universe substance has become our most sensitive instrument for listening to the whispers of whatever lies beyond the standard model, or probing the architecture that supports the scaffold itself. This silent hum is the ultimate guardian of reality. It is the invisible scaffold that prevents the universe from instantly dissolving into a flash of meaningless light. Our journey has taken us from a theoretical crisis, where the laws of physics seem to forbid our existence, to the triumphant discovery of a field that resolved it with breathtaking elegance. The Higgs field does more than simply give particles their mass. It is the cornerstone that allows the entire edifice of the Standard Model to stand, a fundamental actor in the quantum play that makes atoms, stars, and life itself possible. Yet, in solving one profound mystery, it has unveiled others even deeper. The field's precise tuning hints at a multiverse or a hidden symmetry. Its latent energy presents the vacuum catastrophe, a puzzle that challenges our very understanding of nothingness. And its potential connections to dark matter and cosmic inflation suggest it is a thread woven through the entire history of the cosmos, from the first fraction of a second to the distant fate of all things. This is the true legacy of the Higgs discovery. It is not a final answer, but a powerful new question. It transforms our search from proving an idea to exploring a landscape, using the field as our most sensitive instrument to listen for the whispers of physics beyond our current horizon. So the next time you feel the solid weight of an object in your hand, or watch a star shine in the night sky, remember the silent, universal presence that makes it all substantial. Our reality is a delicate and beautiful structure, held together by an invisible force we are only beginning to understand. The quest to map that scaffold, to see what lies beneath and beyond it, is what drives science forward, reminding us that the greatest mysteries are often hidden in plain sight, woven into the very fabric of the world we call home.